is you. There's a cable connected to it. If you've been in an elevator, you understand that when you first get in, doors close, it accelerates upwards until it reaches its cruising speed. And then it will travel at its cruising speed until it gets to the floor you selected, and then it will slow down to a stop. So there's two accelerations in every trip, an acceleration upwards and an acceleration downwards, if you're going up, which is what we're talking about. So right now I want to talk about the upward part of the acceleration. And we'll say that you are accelerated upwards at 1.2 meters per second squared. And let's say that you are, the person inside the elevator has a mass of 70 kilograms. Now, what I want is I want you to tell me the normal force on the person. I've never asked the question before. I've said we're just going to use this for analysis. And that's still true, but I do have a question. What is the normal force on the person? The first thing I want you to do is draw your free body diagram. 4 steps: free body diagram, reference, trig, and Newton's laws. So do your free body diagram, and take a moment and do the free body diagram, and then I'm going to ask you a question about it. So I'll wait like a minute as you read the free body diagram stuff. So the first force, gravity, no problem. So after that, is there anything in contact with the person? Sure, the elevator floor. The normal force is actually what's pushing on the person. Normal force is how you experience weight, by the way. You don't experience the force of gravity. You experience things trying to prevent you from falling, like chairs, floors, stuff like that. You experience those forces. You don't feel your weight. Now I'm going to draw the normal force to be taller or longer than the other forces, because it's the normal force that accelerates you upwards here in the elevator. That's what does the job. A lot of you think that that's, that there's another force here. Some of you have drawn like the tension. But is the cable in contact with the person? No. The cable doesn't accelerate the person upwards. The floor of the elevator does. The cable accelerates the box upwards, and you're in the box. But the cable doesn't act on you directly. So there are only 2 forces. And I'm using my intuition, and you should too, because you're supposed to draw them to scale. The normal force should be drawn longer than the weight. I know the guy's accelerating upwards, and now we have a good argument for why the normal force is the thing doing that. So when I consider that their forces are acting on them have to be unbalanced, I know it has to be unbalanced upwards. So going through the rest of the steps, I should draw in a coordinate system, deciding what's positive and what's negative. I should draw in the x, but the x doesn't matter at all, so I don't really care about it too much. I'll draw it though. The important thing to do now is to recognize that the net force is going to equal ma. This is Newton's second law problem. I know it's second law because they gave me an acceleration. They say very clearly the object's accelerating. Now, this is a set of instructions. It says to add up all the forces, taking into account their direction, and set it equal to ma. So, I have 2 forces. I have the normal force upwards. I have the weight downwards. And I'm going to set that equal to ma. Please notice, I am deciding direction by putting a positive or a negative sign in front of each vector. So I am making my decision about direction here. If it points up, it gets a positive. If it points down, it gets a negative. Now, keep in mind, this is the custom equation designed to solve this problem. So we actually are at the solution. The normal force equals the weight plus ma. Now, just a couple of pieces of information here. ma is the unbalanced part of the force. That's the amount of extra force necessary to accelerate them upwards. The normal force already has to balance their weight. So I'm expecting this number to be greater than their weight. The problem is that 70 kilograms isn't their weight, it's their mass. So to figure out weight, you'll need a little bit of extra information. Weight, which is the force of gravity on something, is equal to mg for things that are close to the surface of the Earth, which is mass times the acceleration of gravity. Be aware, your weight on the moon would be different. Your mass on the moon would be the same. Right? Mass is something about how much matter you have. Weight is how gravity affects it. So g here represents the acceleration of gravity. On the Earth, that's 10. Someplace else, it might be different. Now be aware, the force of gravity is a little bit more complicated than this, but since the acceleration is the same everywhere near the surface, this is what we get to use here. Which also tells me then that normal equals mg plus ma. I could now use this to get an answer that's a numerical answer. I mean, I'll have 70 times 10 for mg plus 70 times 1.2. Don't just put a negative 10 in here. I've been saying that all year, not just to make gravity negative, to be conscious about up and down, about direction. This g isn't negative 10. G indicates direction. We took into account the direction here when we made the weight negative. So don't blindly put in a negative 10, you will get it wrong. But here the answer is going to be 784. But let's look at the units for a minute. It's kilograms meters per second squared. That's what's being multiplied together. This is the unit of force. Kilograms meters per second squared. In physics, we have only 3 units: kilograms, meters, and seconds. Second semester, we'll get charge, coulombs. But almost all of our units are complex units. They're combinations of things. This is a complex unit. Kilograms times meters divided by seconds squared. Saying that all the time is kind of hard, so they do give these things names. That's why you've heard of things like watts and joules and calories, and these are all combination units. And this is no different. This one has a name. We call it newtons. They really stretched for it there. It's a unit of force. The English unit of force is the pound, and you've used pounds before. You think it's something that's the same as kilograms, but it's not. A pound is a force. That's why when you fill your tires with air, you're inflating it to a pressure that's usually in pounds per square inch, PSI, because pound is force. The actual English unit for the kilogram, or the English unit for mass, you've probably never heard of. Does anybody know it? The English unit for mass isn't the pound, it's the slug or the stone. That's the English unit for mass. You've never had your mass taken in slugs or stones. No one's ever written that down before. When you go to the doctor, they take your weight and convert it to kilograms. They're dividing by G to do so. So, this is the answer. 784 newtons. And for the time being, I will write out the word newtons so we know it's a combination or complex unit. Now, what I want you to do is I want you to repeat this problem, because you've done these on your own in some sense, you're never going to get it. And you need to struggle with it a little bit. So I want you to consider 2 times. I want you to consider the elevator still. And I want you to consider the time that the elevator is moving at a constant velocity. So it's accelerated upwards and is now going upwards at 2 meters per second. And then it reaches the desired floor. And when it reaches the desired floor, it's going to slow down with an acceleration of 2.4 meters per second squared. So here it's constant speed, and here is slowing down. So it's moving upwards, but slows down. And here it's moving upwards, but constant speed. I'd like you to find the normal force for each. I'm going to give you guys about 5 minutes to do that. Try them, and perhaps be willing to fail a little bit. Look, the first one, there's a downward force for weight. It's not a surprise. Upward force for normal. There's no difference in the forces themselves, which ones are there, except I know they're going to be balanced. Constant speed means no acceleration. It's part of the law. It doesn't take force to maintain motion. It takes force to change motion. So an unbalanced force causes your motion to change. Balanced forces are fine for something that's traveling at a constant. So the net force will be equal to 0 when traveling at a constant speed. The 2 meters per second is a distraction, and one that will be used against you, I'm sure, on the exam. That means there's only two forces. Normal minus weight, that equals 0, which means the normal equals the weight. The weight's 700 mg. It's not that one I'm worried about, it's the next one I'm worried about. I mean, this one I think most people will get. But I think a lot of people who even have a good handle on it are making mistakes in the second one. The forces are still going to be the same. Weight hasn't changed in any of these. It's still 700. But if the elevator is going to slow down, the net force has to be downwards. It's moving upwards. The velocity has to be brought to 0, so the net force has to be downwards, which means the normal force has to be reduced. Look, normal force is what you feel. You don't feel your weight. People think they do, but you don't. You feel how other things respond to your weight. You feel the pressure on your butt from the chair. You feel the pressure on the floor from your feet. That's the ground pushing upwards. That's you feeling your weight, is by how other things feel against your body. Now I'm saying this because if you've been in an elevator, you know that when you reach the top, you feel lighter for a moment as the elevator slows down. It's not an accident. It's lighter because it's using your weight to slow you down. That's how it works. So when I look at the net force equals ma. No different than before. That's still going to be normal minus weight equals ma. Still the same as before. So normal equals 700 plus 70 times negative 2.4. The acceleration is downwards. And since acceleration is a vector, when it's downwards, I need to take its direction into account. We don't blindly put signs in, but we do have to pay attention to direction. And any value that is a vector value, you need to be extra careful in paying attention to its sign. So, if you work it out now, most of you have found out this comes out to be 532 newtons. Yes, ma'am?
Why was it?
So again, here's my setup. The same as before, you know, in the problem we had last week. I have a 20 kilogram wagon. It's being pulled with 100 newtons of force at an angle of 30 degrees. But in this case, the wagon moves at a constant 1 meter per second. Now I'm saying this because before I said that the ground was frictionless. This one is not frictionless. I'm going to ask you to find the frictional force and the normal force. So I want you to find the frictional force and the normal force. This is not straightforward. Take a few minutes and try and get started. I would try and get your free body diagram drawn before you leave. The numerical answers are here from where we started last week. So I drew the weight. I mean, I clearly have a tension force. They give me this one. It's touching the ground, so there's got to be a normal force. What a lot of you are forgetting is if they're balanced, there has to be a frictional force. Goodbye, have a good day.
If we're doing NHS, do I just